Hi everyone, it's John. So we're gonna work through the week 6 worksheet. This week's worksheet is chemical equilibrium. So question number 1, it says, what does it mean for a system to be at equilibrium? So when a system is at equilibrium, we say that the forwards rate is equal to the backwards rate. You want to make this a little bit more clear. It's the rates of reaction. So how quickly the reactions are happening. So if the forwards rate is just as quickly as the backwards rate, the reaction is not shifting to the left or to the right, and the system is at equilibrium. Number 2, it says, what is the value for Kc if the concentration of carbon monoxide is that hydrogen and CH3OH for the following reaction? So Kc, just as a general thing, is products over reactants with their respective coefficients. So as powers. So we have CO, CO to the first power because it has a coefficient of 1. We have H2 to the second power, and then our reactant, we have CH3OH. And this is to the first power. Then all we got to do is plug this in. So 0.025, 0.013 squared, 0.0028. And then when you plug this all in, you get 1.5 times 10 to the negative 3, or A. Number 3, it says an equilibrium process, the concentrations of products and reactants are equal. This is not true. Concentrations will remain constant at equilibrium, but they don't have to be the same, right, as we see in the previous problem. All right, 4 says changes in temperature cause change in the equilibrium position. This is true, right? It depends on whether or not, if it's endothermic or exothermic. So if you have an endothermic reaction, you can think of it as heat plus whatever else turns into your products. And by Le Chatelier's principle, if you add heat or raise the temperature, it's going to shift to the right. And I should draw this as an equilibrium arrow. It's stuff, and then plus heat. So raising your temperature adds heat. Lowering temperature removes heat. And reaction shifts in accordance with Le Chatelier's principle. And number 5, it says, given the following. So we have these two reactions, and it says, find the value of the equilibrium constant for the following equilibrium reaction. Okay, so you're going to be adding these equations together in some way. Now, what it looks like we're going to want is we're going to want to reverse the first one. Because we have an N2O on the right here, and we have an N2O on the left in the first one, and it's the only one where we have an N2O. So if you reverse the first reaction, we're going to get 2NO is in equilibrium with 1/2 O2 plus N2O. I'm not going to do the state symbols just to save on time here. They're all gases. And then that's the first step, right? So we have N2O on the right side. Now, if we look at the second one we have N2 on the left, we have O2 on the left, and we have NO. Now, if we just add this to the second one, it's going to work out, sorry, to the first one, we're going to get this equation or this reaction. Why? Because in this one, we have N2 on the left. In the second one, second reaction that we're given, we have N2 on the left. So we need N2 on the left from the second one. So we're going to keep number 2 the same. And then add. So when we add these two, I actually do need to write something else. So we do get the correct equation, right? Because the NOs cancel out. 1/2 O2 cancels out on the right. And then we're left with that. Now the KCs for each of these. So this KC is still 4.1 times 10 to the negative 31. However, this KC changes. Why does it change? Because you reverse the reaction. When you reverse the reaction, the Kc is going to become, the new equilibrium constant is 1 over the old one. So it's 1 over 1.7 times 10 to the negative 13th. The reason why this happens is, let's say you have Kc is products over reactants, as you know it. This is not really correct notation. There should be a pi symbol showing things that you're multiplying the products, but doesn't really matter. So this is the Kc, right? Kc of forward. Or let's just leave it as Kc. So if you reverse the reaction, you're getting reactants over your products. Right? Now, how does that change Kc? Well, you're flipping the two, right? So you can think of it as you're flipping the fraction. So before we had Kc over 1. Now this is 1 over Kc. That's one way to think about it. You could also think about it as a complex fraction. 1 over products over reactants. That's equivalent, and that is the same. So 1 over Kc. But this is why it flips, or you take the reciprocal. So when you're flipping the products and the reactants, everything flips as a fraction or in the fraction. So Kc then flips as well. So now for this new one, and I really don't like this notation. Why don't we call this Kc1 and Kc2? And then actually, I'll do it for here, Kc1 and Kc2. That way we can just distinguish between the two when we're talking. So for this new reaction, when you're adding the reactions, what you're going to do is multiply the Kcs. So this is Kc, so let's call it Kc3. It's Kc1 times Kc2. Then you can just plug in the values. So the first one, 1.7 times 10 to the negative 13. Under 1, and then times 4.1 times 10 to the negative 31. You plug these in. And you get 2.41 times 10 to the negative 18th. And that's it for this one. So this is a common thing that you're going to be doing where you're changing the reaction and you have to know how Kc changes with it. 6, it says consider the following equilibrium reaction. Kc is equal to 96.2. The equilibrium constant for the decomposition of PCl5 to PCl3 and Cl2 is what? So surprised this one comes second, but it's the same thing that we just did. So we are reversing the reaction. So the new Kc, we can call it Kc reverse or something like that, or you can think of it like that. Um, I'm just going to say Kc reverse or K reverse. C just stands for constant, but I'm just going to start labeling things in terms of what makes things more clear because the subscripts don't actually mean really anything other than labeling for context. So Kc is the equilibrium constant. So I'm just going to start labeling subscripts just so we can be clear about what we're saying instead of saying that Kc, this Kc, whatever Kc. So the new one is going to be 1 over the original because we flipped it, right? As we kind of just saw in the last problem. So the answer is B. And that's it. 7, it says given the following reactions, calculate Kc for the reaction below. All right. So the first thing to note is for our products, we're going to need 2 of these. 2 of that. Since we need 2 PCl5s. And then we're going to reverse the first one. So that way we can get 5 Cl2s, so 2 plus 3, as well as 2 phosphoruses on the left. And then the PCl3s will end up canceling out as well. So this one, we're reversing the first one. When you reverse the first one, I'm going to call this Kc1 and Kc2. So this new Kc is going to be 1 over Kc1. Now, what do we do with this 2 times, right? So that becomes the next question. When you're multiplying it by something, you're going to take Kc to the power of whatever you're multiplying it by. Why is that? So let's say you have some sort of reaction. So I'll do it up here. Let's say you have K is equal to products over reactants. And actually, let's just make this very specific. So let's say A plus B is in equilibrium with C. So Kc is equal to concentration of A times concentration of B for concentration of C. I could write this more generally using not 1 as the coefficients of each of these, but I think that'll confuse most of you if I start plugging in variables, so I won't do it. So we're going to use 1 for these coefficients and then see what happens to Kc if I double them. Okay, I'm going to call this Kc1. All right, now if I go ahead and double everything, 2a plus 2b gives 2c. It's an equilibrium. So this Kc is concentration of A squared over times concentration of B squared over concentration of C squared. All right, and all I did was double the coefficients or multiply everything by 2. Now we want to compare Kc1 and Kc2. Well, Kc2, everything is squared, right? Everything just got doubled. Kc2, what happened is when we doubled the coefficient, the powers of everything end up double. So that's squared, right? This is equivalent, right? So this is the same as the top one. This is just rules of exponent, right? The square distributes to everything on the inside. Now, if you look at this is Kc1, right? Right, over here. So you can make this relationship pretty clear now that Kc2 is equal to Kc1 squared. So before and after. So before we doubled everything and after we doubled everything. After we double everything, it's the same as the first, but you just square it. So that's where this comes from. If you want to do, if you have everything, right, to the 1 power, 1/2 power or something. So then you're going to get Kc to the 1/2. So I'll make a note over here. So whenever you multiply by a constant C, the new Kc will be the new Kc, and I'll denote this as Kc new, is the old one to the C power. So in other words, Kc new, whatever the new equilibrium constant is the old one some power C or some constant. You can't even make this. You can make it whatever you want. Let's do A. So we don't have so many C's. So that's what it is. So now we go back to this. Right now we've talked about why it's squared. And then all you have to do is plug in everything. So 1 over 0.0667 times 4 squared. And then we end up getting 240. And then we're done. All right, number 8 says at a certain temperature, Kc and delta H is equal to that for the reaction below. Positive delta H indicates that this is an endothermic reaction, thus heat is needed for the reaction to proceed in the forwards direction. 2 MgCl2 plus O2 yields 2 MgO and plus 2 Cl2 gas. Calculate Kc for the reaction. The reaction of MgO, Cl2, okay. And indicate whether the products will be larger or smaller at a lower temperature. So this reaction, this new reaction, is the first multiplied by 2 and reversed. So it's going to be 1 over Kc squared, or the new one, the new equilibrium constant for this reaction is the equilibrium constant. So that's the equilibrium constant for this new one. The fraction comes from reversing it. The squaring comes from multiplying by 2. And you can break this up into steps and do each one at a time. I'm just going to do them all at once, which you're allowed to do. So if you're reversing it, multiplying by 2, multiplying by 1/2, whatever it is, you can do that all at once. So that is the new equilibrium constant. And yeah, now we can just plug this in. So 1 over 0.05 squared is apparently 4.47. Um, it's not. So I think there might be something wrong on the answer key, because this does make sense. So we reverse it, so you get 1 over Kc, and then you are squaring it because you double everything. So this is not correct. This is 400. All right. Um, so that's it for that part. And now because it's endothermic, uh, you're adding heat on the left on that first one. Since we reverse the reaction here, the heat is on the right. So it's exothermic. So by removing heat, it's a lowering temperature. The reaction shifts to the right, so products are larger. And then that's it. This is Le Chatelier's principle. It's not a physical product heat, but you can, for all extensive purposes, treat it like one to do these problems. All right, number 9, it says find K for this overall reaction. We have boron plus hydrogen yields 1/2 B2H6. And then we have these different reactions. So we know we're going to want this one, this B2H6 from the second one, because it's the only one with B2H6. So I'm going to reverse and have it. Because we want 1/2 B2H6. So this is going to be 1 over K2 to the 1/2 power, or 1 over square root of K2. Those are the same. The 1 over part, or the reciprocal part, from reversing the reaction, the 1/2 part from multiplying everything by 2. Right. So we're multiplying by 1/2, so you have to raise the constant by that power, 1/2. Then, so that's it for that reaction. Then let's see, which one has boron? So the first one has boron. So this one we are having. So multiply by 1/2. And then that is going to give us K1 to the 1/2 power, right, for the new equilibrium constant. And then we have H2. So this one, we're going to multiply by 3/2 because we want 3/2 H2 on the left. So again, the rule still holds. We're multiplying everything by 3/2. So we're just going to raise it to the 3/2 power, right? Just follow the same rule. Uh, okay, so now I have all the things in the actual reaction that I do want, but now I have to figure out how to get rid of whatever else. So I think the only thing that's really left, because we did everything right, the only thing that should be left is the water. We need the water to cancel out from this one. And so we need the liquid water to cancel out from that one. Um, and then we also need this water to cancel out. You could do it either way at this point. If you have 4 reactions, let's just pick one and assume it's going to work out. Otherwise, the problem wasn't constructed correctly. So we're going to pick one. I'm just going to balance the liquid just because I think it's easier. So to balance the liquid, we're going to multiply by 3/2 to cancel with the 3/2 H2O liquid from the third one. So we get K4 to the 3/2 power. And if you're wondering why, again, just keep in mind, also these arrows should probably be equilibrium arrows, right? Otherwise, we don't have a K. Um, okay. But then that's it. So, oh yeah, I said if you're wondering why. So if you're wondering why, on this third reaction, right, we have liquid water on the right. That does not show up in this final equation, this final reaction. So we want to get rid of it, right? I have 3/2 because I multiplied this one by 3/2. So to get rid of 3/2 of liquid water, I need 3/2 of liquid water on the left side or on the reactant side of one of these. 4 is the only one with that. So we do 3/2. Then since we're adding all of them, so we add all of them or all of the reactions to confirm we get the correct final one, which we do. I'll leave that up to you to verify if you are suspicious. And then we multiply the Ks, just as we saw, I think, in problem 3 or 4. For the new one. So K1 to the 1/2 times 1/K2 to the 1/2 times K3 to the 3/2 times K4 to the 3/2. It looks like the answer here is C, right, where they're dividing. Okay, formula that relates Kc and Kp, where Kp is equal to Kc times RT to the delta N, where N or delta N is the change of moles of gas from reactants to products in your equation. So since we want Kc, I'm just going to go ahead and divide here by RT to the delta N. That's just algebra, right? And then we can start plugging in stuff. So Kp is 4.6 times 10 to the negative 14. R is going to be the 8.314 constant. T is temperature in Kelvin. 298. And then delta N. So we're seeing how much the moles of gas change. So positive delta N means that you have more. I should probably note this here. So if delta N is positive or bigger than 0, that means you have more moles of gas products than reactants. And if it's negative, you have more moles of gas reactants than products, right? So you're going down in moles of gas. If you have more moles of gas reactants, that's why it's negative. You're going up in moles of gas if it's positive. So if we're looking at this, we have 2 moles on the left from Cl2, and then 2 moles on the left or the reactant side from H2O. So you have 4 moles of gaseous reactants. On the right side, we have 4 moles of gaseous reactants from the HCl, 1 mole from the O2. So we're going from 4 to 5, right? You just can do 5 minus 1. So delta N is equal to 5 minus 1, which is, or sorry, 5 minus 4, which is 1. So 5 from the product side, 4 from the reactant side. So the total change is 1 mole of gas, or gaining 1 mole of gas from reactants to products. So this is to the first power. Then we plug this into the calculator. And we should get, and you get 1.9 times 10 to the negative 15th. And R is 0.0821. 11 says find Kp for the following reaction at 25 degrees C. So this one, you're using the same formula. Kp equals Kc RT to the delta N. Kc is 2.51 times 10 to the negative 2. R is 0.0821. The temperature is 298. We have 2 moles of gaseous products, right? 1 mole of gaseous reactant. So that's just 1. And then you plug it in and you get 0.614. All right. Going on to number 12, it says the following reaction is at equilibrium. And then we're doing certain things and we're seeing what changes. So the first one says, if you take away A, what happens to K? So K is a constant. K is an equilibrium constant. So it's the concentrations of each reactant or product, or really the relative ratio of concentrations of products to reactants at equilibrium. And it's a constant that does not change. So we're going to see things about Q later, the reaction quotient, which is related to K, but it doesn't have to be at equilibrium. So K is always at equilibrium and it's a constant and it never changes. So no change. Constants will never change. Next, it says if you decrease volume, what happens to the amount of C? So if you're decreasing the volume of something, think of it as you're squeezing things down or in. So you're also increasing the pressure. They're kind of synonymous for these types of problems. So if you're decreasing the volume, it's going to shift to the side with less moles of gas. You can think of it as there's less space. So the equilibrium is going to favor things that take up less space. So on this example, you have 2 moles of gas on the left, 2 moles of gas, 1 mole of gas on the right. And so decreasing the volume shifts it to the right, shifts right, since there's less moles of gas. So the amount of C is going to increase. Next, it says if you add B, what happens to the amount of A? So using the Schottler's principle, if you add add something to one side of the reaction. So if you add a reactant, it's going to shift towards the products. If you're adding a product, it shifts towards the reactants. This is how the system relieves stress. Um, the way I kind of think about it is like a pile of sand. So if you add a big pile of sand on one side and you want them to be about equal, you have to move sand from one side to the other, right? Similarly, if you have a hole, so let's say you remove something, then you're gonna have a hole and the other one is flat and you want to make them about equal. So you shovel sand from the other side into the one with the hole until they're about equal. So adding stuff to the reactant side shifts it to the product side, adding it to the product side shifts it to the reactant side, removing something from one side shifts it towards that side. So removing a reactant shifts it towards the product side, removing a product shifts it towards wait, what I say? Removing a reactant shifts it towards the reactant side, removing a product shifts it towards the product side. So if you add B, it shifts it towards the product side, which means you're going to use up more of A, right? Because you have to use up A to have this reaction. So the amount of A is going to decrease. All right, number 13, this is one of the reactions in the gasification of coal is that for each of the following changes, explain the increase. Increase, decrease, no effect. Now the delta H, it's exothermic, so I'm just going to put heat here. As if it were a physical product, it's really not, but it helps with Le Chatelier's principle, in my opinion. On the number of moles of CH4 produced. So if it's shifting towards the right, we're producing more moles of CH4. If it's shifting towards the left, you're producing less moles or you're decreasing the amount of CH4. So yeah, yeah. So that's all we're really checking. Does it go left, right, or nothing? Does nothing. So if you increase the concentration of H2O gas, you're going to get a decrease because it's on the right side. And it's going to want to shift it to the left, right? Because you're adding it. Again, you kind of think of it as a pile of sand. You got to scoop some of that sand to the other side. So you're going to get a decrease because you're adding a product. So it shifts towards the reactant side. Therefore, you use up CH4. So it goes to the left. And I should put this in here. So this is a right shift, left shift, no shift. If you decrease the volume of the container, it's going to shift to the side with less moles of gas. So on the right, left here, we have 4 moles of gas. Here we have 1 and 3. On the right, we have 2. So it's going to shift towards the right. So this is going to be an increase in CH4. If you add a catalyst, it doesn't do anything in terms of the equilibrium. And then D, it says decrease the temperature. So if you decrease the temperature, think of it again, think of heat as like a product, like a physical product. It can be helpful. So if you're thinking of heat as a physical product, if you're removing heat or decreasing the temperature, the reaction is going to shift towards the right, right? Think of it as a hole again, and then you need to dig out some sand and add it to the other side. So removing heat is going to increase it. Number 14 says, what is Q of a reaction? For a reaction profile, does Q change over time? For a reaction profile, does Kc change over time? So we said Kc does not change. And then Q is the reaction quotient. So it kind of tells you relative to K, whether or not the reaction is going to shift left or to the right. So we'll see it in a second. And then Q does change over time. And say Q is the reaction quotient at any one time. So one specific snapshot in time. And Q does change over time. Then 15 says, which way will the equilibrium shift in the following scenarios? Q is bigger than K. K is bigger than Q, and K is bigger than 1. Um, so these parts don't really matter. We're just looking at Q and K. So Q relative to K. So these are pretty irrelevant right now, because it doesn't really tell us how it's changing or how the system is changing. If Q is bigger than 1, you have more products than reactants generally, kind of speaking. If it's smaller than 1, it's generally you have more reactants, but it doesn't really matter what it is because we're comparing Q and K, and it's technically not true what I just said because you're multiplying them and their concentrations and so on. So if Q is smaller than K, what that's telling you, so Q, again, let's say Q is products over reactants. And this doesn't have to be at equilibrium. So it's not necessarily at equilibrium like K. So K is always at equilibrium when you're calculating this. Q is not. That could be, but it's not always. So if Q is less than K, which we see in A, if Q is less than K, then that means that Q is smaller, right, than K, which means that you have a larger reactant, larger number of things on the bottom, because dividing by a bigger number makes the number smaller, right? Just mathematically. So if Q is smaller than K, that means you have more reactants than K does, right? Or more reactants relative to the products than K does. So think of it as you have too much reactants. So this is going to shift to the right because you have too, quote unquote, too many reactants. If Q is bigger than K, right, you have a number bigger than K. So that means that the top is bigger, or your products are larger, right, relatively speaking, to K. So because you have more products than you should at equilibrium, you want to remove some of them. So it's going to shift towards the left. This is too many products. And then Q equals K, there is no change. There's no shift because the system is at equilibrium. So if Q is equal to K, the system is happy. The system is at equilibrium. There's not too many products, not too many reactants. It's just right. Number 16 says, which is favored? Products or reactants? K is bigger than 1. Q is bigger than K. Um, so now this is the part that's irrelevant. Why? Because now we don't really care what's happening to the system, right? We're saying at equilibrium, are the products favored or are the reactants favored? Q in relation to K tells you whether it's shifting left or right. It doesn't really tell you which is favored at equilibrium. So if K is bigger than 1, the products are favored because the numerator is bigger. For B, it's the reactants because you're dividing by a bigger number, right? Uh, KC is equal to products over reactants, and this is only at equilibrium. So Again, bigger than one, you have more stuff on top. Most smaller than one, you have more stuff on the bottom. So if K is bigger than one, the products are favored. 17 says for the reaction CO plus 3H2 gives you those things, H2O and CH4. Kc is 190 at 1,000 Kelvin. If the vessel is filled with these gases such that these are the initial concentrations, in which direction will a reaction occur and why? So all we have to do is calculate Q here. Q. So if we want to see which way it's going to go, because the system's not at equilibrium. So if you're wondering why not use Le Chatelier's principle, well, you can only use Le Chatelier's principle when it's at equilibrium. If it's at equilibrium and then you add something to the system that stresses it, you can figure out which way it goes. If you're just starting out or you just added stuff and has not established equilibrium yet, you cannot use Le Chatelier's principle. You have to use Q. So Q here, again, products over reactants. So products are H2O, 0.025 to the first power, because coefficient of 1, and CH4, so 0.046 to the first power, also coefficient of 1. CO is 0.025. That's one of the reactants to the first power. And then H2 is 0.045. And then this one is to the third power because the coefficient is 3. So when you calculate this, apparently it ends up being 504 once you plug everything in. We can see that Q is less than K, or greater than K, sorry. So there are too many products, right? That's the way you can think of it. So it shifts towards the reactants. Wants to get rid of some of those products. So it's towards the reactants because Q is 504. And that's it. 18 says, consider the following reaction. Solid carbon plus H2O gas yields carbon monoxide and H2 gas. At equilibrium at a certain temperature, H2O gas is 0.12 molar and CO gas is equal to 1.2 molar. If suddenly these concentrations are increased by 0.5 molar, which of the following is true? More products are formed. Kc is equal to that. More H2O will be formed. Since Kc does not change, nothing happens. This one, you can also use Q. You can, yeah, so we can just use Q again here. So first we have to calculate whatever Kc is because we have the concentrations at equilibrium. So at equilibrium, we have products over reactants again. So CO and H2 are 1.2 molar. H2O is 0.12. So you get 12. Let me plug this in. So Kc is equal to 12 when the system's at equilibrium. Now we can calculate Q. So after we go ahead and add 0.5 to each of these, we get Q is equal to, and this is 1.7. 1.7, we're adding 0.5 molar to everything. 0.62. We get Q is equal to 4.66. So notice B is Kc. That's not true. K is 12. Q is 4.66, right? So after you increase them, because they're no longer at equilibrium. So that's not true. We do see here that Q is less than K. So there's too many reactants, and it's going to end up shifting towards the right, or shift towards the products. So more products are in fact formed. So B is not true because that's Q. C is not true because that's a reactant. AC does not change, but that doesn't mean nothing happens. All right, so number 19 says consider the following equations. We're given this equation, we're given Kc, and we're given initial concentrations. And we want to figure out what the equilibrium is after this whole thing kind of shifts around. So what we're going to do, there we go, is do an ice table. So an initial, change, and then equilibrium table. So what we start with, what the change is going to be, and then what the end is. So first we start with the concentration, 0.04 for the N2O4, and then 0 for this. Now what is the change? So the change here is going to be minus X for N2O4 and minus 2X for NO2. X is going to be the amount of moles of N2O4 that we're using up. So for every 1 mole of N2O4 we use, right, there's a coefficient of 1. We get 2 moles, oops, and this should be a plus, 2 moles of NO2. So we don't know what X is. It's just some number that it's going to change by. We don't know yet. We're going to calculate it. But whatever X is, so however many moles of N2O4 we're losing, or molarity, we're going to get twice as much for N2NO2. So the end here is 0.04 minus X, and then this is going to be 2X. Now we can go ahead and use our Kc. So Kc is the concentration of NO2 squared over N2O4 to the first power. And this is at equilibrium, right? So Kc is equal to 2x squared over 0.04 minus x. Now you have kind of two things here. So I'm going to go with the first one, and then hopefully it's fine. I'll talk about it if it's not. So we're going to assume that x is less than 5% of 0.04. So we're going to assume that x is a lot smaller than 0.04, or it's negligible. So that means that 0.04 minus x is about equal to 0.04. It's like 10 minus 1 to the negative, 1 times 10 to the negative 10th is not technically 10, right? But it's pretty much 10. It's close enough to 10. So it's really not, but it's close enough. So we're going to use that to try to make this problem a little bit easier, math-wise. If you don't do this, you're going to have to distribute stuff, distribute the Kc, then use the quadratic formula, and it can be a kind of a big pain. So that's why I'm doing this. Then we go ahead and simplify the top. We get 4x squared over 0.04. And simplify that. So that's 100, 100x squared. And then we can plug in for Kc. So 5.8 times 10 to the negative 3 is equal to 100x squared. Solve for x. Now this is just algebra, right? It's fairly simple. 5.8 times 10 to the negative 3 over 100. And you're taking the square root, positive square root, because you can't have a negative. Concentration And then we get 5.8 times 10 to the negative 3 over 100. Get 0.0076. Now we have a problem here. So the problem here is that 0.0, oops, yeah, 0.0076 is bigger than 5% of 0.04. So the thing that we started with. So now this approximation is not valid. So this is something that you want to check if you're using the approximation. So because the approximation is not valid, we basically have to do this whole thing again. So sorry for those of you watching, but I think that is a good lesson. So we use the approximation, sadly didn't work. So now we're back to here. Now we get to do a whole bunch of algebra. So I'm going to leave this in terms of KC. You can plug in if you want. I think to be honest, I think that's a poor idea just because it's so easy to make a calculator error with KC. Like you're multiplying 5.8 times 10 to the negative 3 by 0.04, you're carrying it to the x, and then you have to keep track of all these things. It's easy to just drop something instead of just store it as like 5.8 times 10 to the negative 3 as x in your calculator or y or whatever, and then plug it into the quadratic formula. Make it a lot easier. So I'm going to leave it as in terms of KC. Again, just to make this way, way cleaner than it otherwise would be. So we have KC times 0.04 minus x is equal to 4x squared. I'm going to distribute and then get everything on the same side. So 4x squared minus kcx, right? Distributing the kc. Actually, wait a second, because I'm subtracting that. So give me a sec. Let's actually go a little bit over here. So kc times 0.04 minus kcx is equal to 4x squared. So we get 4x squared plus kcx minus 0.04 kc is equal to 0. Right, we have a quadratic equation and we can use the quadratic formula. If it's not quadratic, you can't use the quadratic formula. So if it's cubic, you have to use the approximation, and then you have to see if it's valid or not. If it is valid, great. If it's not valid, you can't do the problem. I don't know how you would do that unless you're gonna graph it on your calculator or something. So if it's not quadratic and the assumption does not work, assume you can't solve it. Assume that you just can't do it. So yeah, if it's linear, then it works. But if it's, yeah, if it's not quadratic, if it's cubic or above, and the assumption doesn't work to simplify it, then you can't do it. All right, so now all we have to do is plug into the quadratic formula. So x is equal to negative b, so kc, plus or minus the square root of b squared. So kc squared minus 4 times a, which is 4, times c, which is negative 0.04 times kc, all over 2a, 2 times 4. Now, do note, we are only going to use the plus since the minus gives a negative number. All right, why? Because negative kc is negative, minus something is negative divided by a positive, which is negative, and you can't have a negative concentration. So we're going to use the plus here. If you're not sure why I'm doing it, just do both and then see which one is positive. So give me 1 second to plug this in. And then we get 0.0084. Yeah. And this is units of molarity from over here. So we're almost done here. Now notice it's not that much different than the one before, right? It's about 0.005 of a difference. Or sorry, 0.0005. But that's still about a 6% difference from the two answers. So it's not insignificant. So now what we can do is plug this back in. So we want to find N2O4 concentration. So 0.04 minus 0.0084. And then we get 0.032 molar. And then that's it. All right. Yeah, and the reason the approximation didn't work again is just, I think 0.007 is like, I think I calculated is like 20% or something like that with 0.04. So it's way too big to assume that it's a good enough approximation, in I guess in my opinion. All right. 20 says consider the following gas phase reaction at 25 degrees Celsius. We have that. We have the moles. They're placed in a container, a 1 liter vessel. It's allowed to react. At equilibrium, there are 1.587 moles of N2 gas in the mixture. What is Kc for this reaction at 25 degrees Celsius? So for this one, we're going to do another ice table. Now, it's not um, as super straightforward as we saw before, since we're going to have to use a few different formulas here. So the few formulas we're going to have to use is we're going to, since we have gases, we can calculate Kp, and then we're going to calculate Kc using that formula that relates Kp and Kc that we used before. And then to use Kp, we are going to need the partial pressures of each gas. So it's the partial pressure of the products of each gas in this case. So it's partial pressure of HCN, and we're squaring it. So it's kind of like the concentration, except just in terms of pressures, partial pressures. En2 P C2H2, and then that's it. So we're going to need these partial pressures. Now, how do we get partial pressures? Well, we have moles of gas, right? We're going to need the moles of each gas at equilibrium. Then once we find the moles of each gas at equilibrium, we're going to calculate their partial pressures based off of the total pressure. We get the total pressure for PV equals nRT because we have the total moles of gas at equilibrium. We're going to find out what that is. We have R, we have T, we have the volume as well. And then we can use mole fractions to figure out the partial pressures, right? So as you've probably seen the homework, you should have seen it by now. The partial pressure of any gas is the mole fraction of that gas. So moles of that gas divided by the total times the total pressure. So let's get this started. So we start with the ice table. N2 plus C2H2 gives 2HCN. So here we start with 1.6 for the nitrogen, with 1.75 for the C2H2. We don't start with any HCN. Then let's see. So for the nitrogen, we know there ends up with 1.587 moles. 1.587. So whatever is here we need to get, and then we actually change this. Change the color to blue. We're going to say blue values are given. So whatever the change was, it's going to have to be 1.6 minus because we're losing stuff, right? Shifting to the right, there's nothing there. It's going to have to be 1.6 minus something gives me 1.587. So what is that? It's 0.013. So we're going to have to subtract 0.013 of moles of nitrogen. Then we can use this to relate it to everything else. So that means we're also losing 0.013 moles of C2H2 because we use them in a 1-to-1 molar ratio. For HCN, we're gaining 2 times 0.013 because it's a 2-to-1 molar ratio. And then for C2H2, we end up with 1.737. Right? These are all in terms of moles, by the way. And this is 0.0226 moles. So now we have the moles of everything at equilibrium, right? Now we can plug this into PV equals nRT. So we have the total pressure is equal to the total moles of gas times R times T over volume, PV equals nRT, right? Divided both sides by V. Then you can plug in all the numbers. So the total moles of gas, we're just adding up everything that we just calculated. So 1.587 plus 1.737 plus 0.026. R is 0.0821. Then this is at 298 Kelvin. The volume is 1 liter. Then when you plug this all in, you get 82 ATM. All right. So now we have the total pressure. And now we can finally calculate the Kp from the partial pressures, which is what we wanted to do in the beginning. So then we can then relate it to Kc from that formula. So now with Kp, the partial pressure of HCN is the mole fraction of HCN. So 0.026 over uh, the total moles, which ends up being 3.35 when you add them all up, times the total pressure, which is 82, right? And if you need the formula, right, here it is. So P of X is equal to moles of X over the total moles times the total pressure. So I'm just plugging it in for this, for each of them. So partial pressure of HCN is moles of HCN divided by total, divided times the pressure. That's squared from our equation. And then for the partial pressure of nitrogen, we have 1.587 over 3.35 times 82. We have 1.737 over 3.35 for C2H2 times 82 on the bottom. Then when you plug this all into your calculator, you should get 2.45 times 10 to the negative fourth. And then we can use the formula Kc is equal to Kp over RT delta N. Just remember, we got it from the formula we used before. Kp is equal to Kc RT delta N. Just had to do a little bit of algebra. Just one step, divide by RT to the delta N. And then we just plug this in. So 2.45 times 10 to the negative fourth for 0.0821, oops, times 298 Kelvin. Then the change in the moles of gas for this equation is, or this reaction is Oh, look at that, it's 0. So we have 1 here, 1 here, and then it goes to 2. So delta n is equal to 0. So it's 2.45 times 10 to the negative fourth. And then that is the answer. So Kc is equal to Kp if delta n is 0. Math-wise, right? Because anything to the 0 power is 1. All right. That's it for this one. Then we have 21. So that one's quite involved. I'd say that one's probably the hardest one in this whole sheet. That's a good question. 21, sorry. 21 says you have 0.075 moles of N2 and 1.2 moles of H2, and they're placed in a 3-liter container. When the reaction is that reaches equilibrium, which of the following is true? So when the reaction reaches equilibrium and the concentration of hydrogen is equal to that, we can just do another ice table here, kind of doing what we did before. I'm kind of, again, also surprised that this one came second because this one's easier than the last one. I feel like it would have been easier to do the previous one first to instill certain concepts, or sorry, do this one before the previous one first to instill certain things. So keep in mind as you work through these worksheets, if you're watching this, sometimes the order is not really representative of the difficulty on these worksheets. Like I would personally say do 21 first and then 22 and then go for 20. I think that would make more sense personally. So we have N2, the initial molarity moles of N2. Oh, wait a second. Initial moles of N2 are going to be, or sorry, this is a molarity. The initial molarity of N2 is 0.25. So the molarity here is the moles over liters. So still kind of the same as before, except with a gas instead. Then for, 2575 divided by 1. For H2, it's 0.4. And then for H2, we know it ends up at 0.1. So again, just keep in mind, you have to keep this thing in the same units. So if you're working in molarities, make sure you're keeping it in molarity. If you're working in moles, make sure you keep everything in moles. And then we start presumably with 0 of this. So then we just do everything else. So for hydrogen, we know that we're going to have to go from 0.4 to 0.1. Now we are losing 3 because of the coefficient of 3. So 3 times something because of the ratio. So 3 times 0.1 gives me 0.1 if you take it away from 4. So that's that. And then we can use this for everything else. Minus 0.100. This is plus 2 times 0.100. So this is 0.200. And then this is 0. Oh, wait, no. Sorry. This is a 2.5. I don't know what I'm doing right now. That's a 2.5. 0.75 divided by 3, not the coefficient by the liters. Sorry. So I was right in the beginning. Then I second guessed it. So 0.25 minus 0.1 is 0.15. And then this is it. So now I have all my concentrations. So at equilibrium, the concentration of NH3 ends up being 0.2. And then that's the only correct one. Okay. So you can do these ice tables and then determine what the change is for one thing, if they give you an initial and an end, and then you can use that change for that one thing for all of the other things in the reaction, right? And then you can calculate how much they change and how much they are, or what they are at equilibrium. Right, 22, it says a mixture containing 0.075 molar HCl and 0.033 molar O2 is allowed to come to equilibrium at 480 degrees Celsius. At equilibrium, the concentration of Cl2 is that. What is the value of Kc? So we're doing the same thing here. We're starting with 4 HCl. So let me write out this thing. We're going to do another ice table. So we start with 0.0750. I'll do it in blue for whatever is given. 0.0750 molar HCl. We have 0.00330 molar O2. We don't have any of the products from what they tell us. And then we start with, we know we have 0.03 molar Cl2 at equilibrium. Okay, and I think that's all our givens. So now we can find the change for Cl2 first, right? We have the initial and the end. So with Cl2, we're going to be adding 2 times something, right? The coefficient. So it's kind of like the 2x's we saw before, except with a number now. So 2 times something is equal to 0.3, or O3. That is 2 times 0.015, right? You could even do it as 2x equals 0.30, divide both sides by 2. That also works. But yeah, if you want to like write it all out math-wise, it makes sense of it like that. So then I'm just going to fill in the changes for all of these now, since I know the change, or x, is going to be 0.015. It says minus 0.015 minus 4 times 0.015. Then I can fill in all the blanks for equilibrium. So 0.015. And then this one is 0.018. And this is 0.030. And then all we have to do is plug this into Kc. HCl to the fourth, 2.03 squared, 0.03 squared, 0.015 to the fourth, 0.018 squared. Then when you plug this all into your calculator, you should get 890. And then that one's it. Okay. So again, you want to get comfortable with these ice tables, comfortable with manipulating these. Again, I'll even put in the math here. 2x equals 0.030, x is equal to 0.015. So just make sure you know how to do those. You're going to see these come up a lot. Last one, 23. It says for the decomposition of ammonium carbamate, we have Kp at a certain temperature is that. A solid sample of ammonium carbamate is introduced into an evacuated container, and at an equilibrium, some solid remains in the container. What is the total pressure in the container for every 1 mole of the starting material? So first thing we want to do is write out our Kp expression, since they give us Kp. So we know Kp is the partial pressure of the products to the power of their respective coefficients. So P and H3, this is also not balanced, by the way. Because there's 2 nitrogens on the left and there's one on the right. So no chance that's balanced. You need 2 of those. So make sure you check the equations first. So this is partial pressure of NH3 squared times the partial pressure of CO2. And then the solid doesn't exert a partial pressure because it's a solid, it's not a gas. So over nothing or over 1. Okay. So now we have to think about how we can relate the partial pressures to one another. So the way we can relate these two, because we're kind of stuck here, unless we can. We have KP and we don't have any way to talk about other things or use anything else. So what we can say is gases exert a partial pressure, and this is true, based on the number of moles, right? So it doesn't matter what molecule it is, it's just based on how many moles of that gas you actually have in the container. So if you just put a solid into the container, right, assuming there is no NH3 or CO2 in the beginning, that's an important distinction. Assuming there's none of those in the container to start with, as equilibrium establishes or as they are produced, we can say that the pressures can be related like this. The way they're related is the partial pressure of NH3 is going to be twice the partial pressure of CO2 because there's 2 times the amount of moles of NH3 produced, right? If you look at the equation, that's balanced. If you look at the balanced equation, you produce 2 moles of NH3 and only 1 mole of CO2. Therefore, when it comes up to equilibrium, there has to be twice as many moles of NH3 than CO2, which means that the partial pressure of NH3 will be twice that of CO2. So now we can plug that in. So Kp, and this is 2 times the partial pressure of CO2 squared times the partial pressure of CO2. You can simplify this out. This is 4 times the partial pressure of CO2 cubed, right? Do a little bit of algebra, right? Divide both sides by 4 and take the cube root. So the partial pressure of CO2 is equal to Kp over 4. You're taking the cube root or to the 1/3 power. And then you plug that in and you get 0.0246 ATM. Okay, so then that's it. And we plugged in the Kp value of 0.0596, so I just didn't write it in. Now we know the pressure of NH2 is equal to 2 times the pressure of CO2, right? We just calculated that. Point 0.492 ATM. When you plug it all in. And so the total pressure is going to be equal to 0.0246 plus 0.0492, which is 0.738 ATM, right? Because just remember the total pressure is equal to the pressure of every gas. So the pressure of NH3 here, plus the pressure of CO2. And then that is your answer, A. All right, so that's it for this video. I hope it helps, and I'll see you again in the next one.